Our next step is going to be to evaluate the conditions coming out of the turbine and the fan. Since we are dealing with a mixed turbofan, these two properties are linked together because we know that the discharge of the bypass duct coming from the fan the pressure there has to match the discharge pressure from the turbine. Unfortunately, unlike the ideal engine where we're able to come up with a nice little, well, bigger but closed form expression for determining the fan pressure ratio directly from other properties, here we're going to have to iterate because we have too many effects or simultaneous effects of changing properties along with our multivariable problem. So we'll begin the analysis here with a energy balance on the shaft. This is our first linkage between the turbine and fan. We know that all the energy being supplied to both the compressor and fan has to be balanced by work coming out of the turbine. So here we can say that the mass flow rate of the core, m dot, times Cp, and here we're going to call it Cpc because we're going to have to track each component. Although we treat the specific heat as constant within a component, there are different values of specific heat for each component. So this is representing the compressor times Tt3 minus Tt2, and then that plus the mass flow rate through the fan is going to be the core mass flow times our bypass ratio, alpha, times CPS, which is going to be the specific heat through the fan, TT7 minus TT2. This is all going to be equal to our work coming out from the turbine, which has our mechanical efficiency, times the mass flow rate through the turbine. This is really going to be our core mass flow rate times 1 plus F, our fuel to air ratio. So the difference here is it's core airflow plus the mass flow of fuel. So we're going to use that turbine total mass flow rate times CPT, and then times TT4 minus TT5. And unfortunately in here we have multiple unknowns. TT7 and TT5 are both variables we're trying to solve. So it tells us we definitely need another equation to be able to link those together. And we have the added problem that CPC is fixed because we already know TT3 and TT2, but we don't know, since we don't know TT7, we don't know CPS. Since we don't know TT5, we don't know CPT. So there's still a lot of things that we need to figure out in order to be able to solve this balance. And so we're going to do that, as I said, by integration. To set that up, we'll solve for TT5 and say that they can be calculated based on TT4 minus the mass flow rate of the core times the specific heat times the compressor specific heat times Tt3 minus Tt2 plus m dot alpha CPS times Tt7 minus Tt2, all of that over our denominator is going to be the mechanical efficiency, A to M, times the mass flow rate through the turbine times our specific heat through the turbine. So in order to solve for TT5, we're going to have to start out with some guess for TT7. And the best way we have to get to a reasonable guess for TT7 is actually we're going to guess a fan pressure ratio, guess that pi f, and then from that we can determine our ideal temperature ratio, tau f prime, which of course is equal to pi f times gamma minus 1 over gamma. But once again, we don't know what gamma will be here because in the fan we're going to look for gamma at the average of TT2 and TT7, and of course we don't know TT7 yet. But we can go from there to calculate the ideal TT7, which is going to be again just that tau f times TT2. And then we can also bring in our definition of the fan efficiency, which again is going to be our ideal temperature change over the real temperature change. We can then calculate TT7 by reorganizing this equation. Say TT7 is going to be equal to TT2 plus TT7 prime minus TT2 over our fan efficiency. So based on our guess of pi f up above, we can get to a value of TT7, which we would then take the answer from that and substitute it into our energy balance to get a new value of TT5. Once we know TT5, we can easily, or we have a nice expression that lets us calculate the turbine pressure ratio pi t based on the expression just 1 minus the turbine temperature ratio, tau t, over our turbine efficiency, eta t, with that whole thing to the gamma over gamma minus 1. And remember that tau t there is equal to TT5, which we just calculated, over TT4, which is given to us. But we will have to iterate for our value of gamma. We were given that the turbine efficiency in this problem is 0.91, so we're good on that one. And so based on our values, we can come up with the value for pi t, and from there we can calculate the turbine discharge pressure. PT5 is equal to pi t times PT4. At the same time, we can calculate the fan discharge pressure, PT7, based on the value of fan pressure ratio, pi f, that we guessed at the beginning, times the fan inlet total pressure, PT2. And then we can propagate that down through the bypass duct and find out the total pressure at the exit of the bypass duct, PT 7.5, is going to be equal to our total pressure ratio for the bypass duct, pi u, times PT7, the fan discharge pressure. And again, we were given at the beginning, that's one of our performance parameters, that the bypass duct pressure ratio is about 0.99. And so this gives us a way to determine the turbine discharge pressure and the bypass duct discharge pressure. And if this engine is going to work, we've said that those total pressures have to match. So we're looking for PT 7.5 is equal to PT5. And we're actually going to keep iterating here and adjusting our guess of pi f until this equality is satisfied. So we have a pretty big iteration loop. It starts way back at the top with our guess of pi f and works down through calculating TT7, then TT5, and then our turbine pressure ratio, and then our turbine discharge pressure and bypass discharge pressure, and seeing if they match. So rather than do all of those calculations by hand every iteration, along with iterations to make sure that our gamma also is set for the correct temperature, it's easier to put all of that together in one big iteration here. You can do this in MATLAB, or this example is from Excel, but it's just hopefully to make it a little easier to visualize. And so you can see on the left side here, we're guessing a value of pi f. We're calculating, or at the beginning, we're actually guessing values of CP and gamma as well. And so we are working with those properties to calculate our temperature ratio for the fan, which gives us the ideal temperature and real discharge temperature from the fan. At the same time, we use that to calculate our TT5, the turbine discharge temperature, again based on kind of estimates of what our real properties should be for the turbine. And once we know the turbine temperature, we can calculate the turbine pressure ratio and turbine discharge pressure. And then we can get PT7, the fan discharge pressure, again just directly from our guess of pi f over here, and with the losses in the bypass duct, we can calculate the pressure at the duct exit. And so you can see, if we want those to match up, well, on the first iteration, we got a difference between a 15.8 psia in the core and 6.77 psia on the bypass duct. So we need to keep adjusting our guess for pi f until that converges. So we come down to the next line, and rather than doing successive substitution, this is going to use the Regula-Falsi method from Appendix G2 in the book, because this will give you a little faster convergence and makes it a little more stable, keeps your guesses from going far afield where you can get undefined answers if you put in the wrong value of pressure ratio. So we make another guess here and basically repeat the whole process, but using maybe improved values for the air properties here based on the previous calculations. And so that one is also way off, but in the other direction now. We used to have the turbine was much higher than the bypass. Now we've got the bypass much higher than the turbine. So we'll have the Regula-Falsi will help us improve our third answer. This is actually where we're starting to iterate. So it picks 2.28, and right away that, as we're converging, is going to get us much closer. So we used to have a difference of 9 and 8 psia at the exit. Now we're down to 1.6. Next iteration we're down to 0.45, and very quickly you'll see it converges down here to the end where they'll agree within 10 to the minus 8th, or very near to 10 to the minus 8th. So we basically, after the third iteration, we're always going to be updating our guess of pi f using this Regula-Falsi method. And we can see as we go down, it doesn't take long for our air properties to converge. Once kind of these shaded areas are showing where the air properties are still converging, and once they're converged, it also doesn't take long for our value of pi f to stop changing, and our other parameters to stop changing as well. So we can say, okay, our converged answer here is going to be TT5 is equal to 1544.157 degrees R. Our PT5 at the discharge pressure of the turbine is going to be 9.674 psia, and of course the duct exit pressure will match that, equals to PT 7.5. So we're now ready to continue on through the core, or the bypass. I guess we should also put down TT7 is equal to 566.816 degrees Rankine. So that gets us through the fan and the turbine. We're ready for the mixer and the nozzle next.